Now let's try some some arithmetics for a while. So we have defined a bunch of numbers, and we also defined two strings. What we can do is to sort of print out, for example, the summation of two numbers. For example, if we do I plus say LD, that's the summation of two numbers, 1 plus 3.1415926. So it should be 4.1415926. And we can also do this. For example, S1 plus S2. So S1 is a string, S2 is another string, and you can actually add two strings together. And in this case, the result is going to be a concatenation of two strings. So in this case, we're actually looking at the plus sign, the sum symbol. The sum symbol, it can apply to two numbers. In this case, it's going to do an arithmetic sum. It's going to do an add. But if you apply the plus sign on two string string objects, it's going to do a string concatenation. So in this particular case, what we say is that the plus sign is overloaded. It's an overloaded operator. So it's overloaded in the sense that you can use it for both the numbers and also on strings, and it's gonna the meaning of the sum is gonna be different if the input parameters, like is depending upon the input parameters, either it's a string or a number. It's the behavior of the plus sign is gonna be different. So that's what we call a overloaded operator. It allows you to use the same operator on different kinds of input parameters. Again, let's save it, build it, and then let's give it a run. So this is a sum of two numbers, and then this is a sum of two string characters, two character strings. So now let me add two more comment lines. I'll just say this is operator overloading for plus operator overloading for integer, for numbers, plus operator overloading for strings. Here we have defined a vector. It's essentially an array, but it has more features than an array. And in C++ language, we call this an object. And this object is an instantiation of the vector class. In fact, it's a vector int class. So what we say is that A is an instantiation of vector int class. So one of the features about object-oriented programming is that you can define your own data type, and together with your own data type, you can define functionalities, like functions that works on your data type, and those things are bundled together into a thing that's called a class or struct. A class or a struct is basically a composition of data and also functionalities or functions that can act on those data. So a class is a certain encapsulation of data plus the functions that can act on the data. And a vector int is a templated class, which means that the the data that's stored in the vector class is flexible. You can specify the kind of data that's going to be used in the vector class. And the kind of data that's going to be used in this particular instance is called int, is an integer. So you can imagine you can also define vector float, for example. So let's call this AI, and this call this AF, for example. And then 1.1, 2.2, 3.3, 4.4, 5.5, for example. So a templated class allows you to specify what kind of data, the type of the data that's going to be stored in this particular class. And you're going to see that this kind of angular bracket is actually quite useful. This kind of templated thing works not just for classes but also for functions. We're going to look at one example of a function a little bit later, a templated function a little bit later. But for now, all we have to sort of understand is that this thing actually represents, this vector int actually represents a class, and AI represents a instantiation of that particular class, and AI is an object of vector int, and AF is an object of vector float. So what I was telling you is that it's an array. So an array has a size, has a length, essentially an array. So how do I actually obtain the size of, for example, AI? Suppose I sort of did lots of operations on AI and I lost track of how many elements are now inside of this particular array AI. So how do I actually get access to the size or the current size of AI? So here I'm typing AI and then followed by a dot, and then I'm just gonna wait here. The IDE is gonna bring up a drop-down menu. The drop-down menu actually contains all the functions that you can invoke on this AI project object. On this object. So what I was telling you is that a class is some kind of combination of data together with functions that can act on those data. So here it's actually the IDE is actually giving you a list of all the functions that can act upon AI object, the data that's stored in the AI. So we're gonna scroll down. And we're gonna look for a function that's called size. So here it's actually, the IDE is actually telling you how to call this particular size function. You don't really have to give it any kind of input. So it's a size void. If you just double click on it, then the IDE is going to insert this function for you. So AI.size is going to actually return the size of the AI array for you. And what you have to do is to, you can do two things for now. For example, you can just print out the size. And in this case, you can actually look at what the size actually is. Maybe we should just do that and build it, and then let's look at what's actually the output. So it's telling you the size is 5. So AI has a size of 5 because it was initialized with 5 elements, that kind of thing. So another thing that you can do, let's comment out this line. Another thing that you can do is to actually store the size into a variable. Let's call this variable ASZ, for example. And then ASZ equals to AI.size. But we have to, because this is a new variable, we have to give it a type. So we'll ask the compiler to figure out the type for ASZ for us. So after I typed in auto, if you move your cursor to ASZ, it's actually displaying what's actually the type for ASZ. So what you can see is that if I press F2 at this point, what you can see is that the type is not so simple. It's actually a quite long type, but that's the sort of the compiler derived type. So this sort of double colon is called a scope. A scope means that So for this particular example, it means that size type is a name that's defined within this scope, and this particular thing is a name that's defined within this scope called std. So ASZ looks like an integer printed out have 5, right? But it's actually has a quite long type, and in particular the name of this type is called size underscore type actually. So if you actually want to write the correct type by yourself, you're gonna have to first know what AI.size is gonna return. That's the first thing that you have to sort of figure out. A second thing is that you have to type that very long type name before ASZ. But if you use auto, it's very little typing, and you're guaranteed that the type of ASZ is going to be correct. So that's ASZ. So now we can just use this ASZ now. What I can do is to print some text. Size of AI is this way. It's going to give me some give user some information about what ASZ actually is. so that's how you can actually call a particular function that can act upon a particular object. You use a dot, and then the syntax for calling this kind of function is basically the same as calling an ordinary function in C or C++. You have a parenthesis, which is going to sort of host all the input variables, and if you don't have any input variables, it's just going to be empty, and then equal to, and then you assign the output of this particular function to some kind of variable. So basically that's how you can call a function in C and C++. The definition for this particular function is actually quite similar in terms of format as this particular function, the main function here, right? You also, in the main function, you also have the parentheses, and then you have a return type. The same is true here. The only thing that's different is probably the name. For here, you just have a name that's called main. But for here, the name of this particular function is called AI.size. You have a dot in between that actually means something. It means that it's a function that's defined for this particular object, AI object. So if we actually build it and then run it, size of AI is 5. Another possibility here is that you use your own type. For example, if you want to use an unsigned int. So we looked at the int. Int is a type that's going to guarantee to be an integer. A unsigned int means that it doesn't have a bit to account for the sign of the integer. So it's always going to be positive numbers, because you know the size is either 0 or some number that's larger than 0. So you can just use an unsigned int instead of just an int. Of course, you can also just use an int. It's not a problem. But unsigned int is kind of more appropriate for this particular example. So basically, you are actually assigning the output of AI.size back to a unsigned int, ASZ. The result is still going to be correct, but the computer has to do a little more work, because you know that AI.size is going to return a type that's different from unsigned int. Actually, it's going to return a type. So what's going to be the type that's going to be returned? So if you actually look at the size function, so let me suppose I type the dot again, and then I'm going to bring up the drop-down menu, and then let me just navigate to the size function. That's the size function. So that's how you can call it. And then you have a colon, and then the stuff that's behind the colon. is actually the return type. So that's going to be std colon colon vector, this thing, and then colon colon size type. That's going to be the actual return type. So what the computer is going to do is that it's going to convert this type implicitly to an unsigned int. So in fact, the computer is going to do an implicit type conversion for you. So that's going to involve some extra work. The result is still going to be correct. The result is still going to be correct. But you have to realize that there is an implicit type conversion here that's carried out by the computer. And if you actually use auto, there's no type conversion. It's just the ASC is going to be just defined as that output type, as you can see, std colon colon this bunch of things, and then colon colon size underscore type. So there's no type conversion here. Now let's try to sort of print out the first element and the last element in the array AI. So what we can do is just for now, let's give it some first element. I'll just say first element, and then what I'm going to do is to use AI. And then how do you actually index into an array? The first element is going to be 0. Again, C and C++ array are 0-based indexing, so it always starts from 0. And then you enclose the index in a pair of square brackets. And then use the end of line. And then I'm going to do last element. But what's going to be the index for the last element? It's going to be the ASC, the size subtract 1, because it's 0-based. And then let's just build it, save it, build it, and run it. So it's telling me that first element is 1 and the last element is 5. That's correct. So that's how you can actually index into an array by using numbers. It's a 0-based indexing scheme. It starts from 0 and ends with the size subtract 1. So that's how you can actually access the elements inside of an array or a vector. So the AI vector now has 5 different values in it, and the size of AI is 5. The first one is 1. The last one is 5. So suppose we would like to add more elements to this vector, to the AI vector. How can we actually do that, right? How can we actually do that? So here I'm going to add a few more lines. I'm still going to bring up the drop-down menu so that I can choose my functions from. The function that I'm going to choose is called pushback. It's called pushback. It's right here, and it's actually telling you how to use this particular function. So it takes like one input. The whole thing, that very long thing, is just some kind of value type, and then followed by a number. And then it returns a void. Returning a void means that it doesn't return anything. So I can just use that function like that. But I'm gonna give some value as the input. I'm gonna give the number 6. So AI.pushback6. This statement is gonna put the number 6 at the end of the current vector AI. So the vector is gonna become 1, 2, 3, 4, 5, 6 instead of just 1, 2, 3, 4, 5. So let me put back one more number, 7, suppose. Right. And now let's see how the output is going to change. You can imagine how the output is going to change. So the size of AI is going to become 7 instead of 5. The first element is still going to be 1, but the last element is going to become 7. So let's just build it and then run it. So the size of AI is now 7. The first element is 1 and the last element is 7. So you can sort of see how you can actually add new elements into a vector. In practice, you don't really want to sort of push back one element at a time. You may want to put the pushback into a loop or something, and then you may want to get those numbers not from sort of the source code, but from a input file, for example. You read the input file and then assign values to all the elements in AI, and then But one particular thing that you have to sort of pay attention to is that this pushback actually allows you to dynamically grow this particular AI, this particular vector. This is a functionality that's not available by the static array. So in the middle of your calculation, if you decide that AI is not big enough, you can just use pushback to grow it to a new size. In our case, we actually it was initialized to be just with 5 elements, but we grew it to like 7 elements in the middle of the code. So vector has this kind of advantage compared with the traditional array. Array has a fixed size. You don't really a static array has a fixed size. You cannot really change the size. If you want to sort of use dynamic array, you have to do memory allocation on a heap by yourself by using malloc, calloc, that kind of a statement in C. But vector allows you to grow the vector, to grow the array dynamically based on the situation, based on how the results from previous calculations, that kind of thing. And all those kind of memory allocation stuff are encapsulated in the object itself, in the class, so you don't have to worry about the memory allocation, that kind of thing, and you can just focus on writing a readable code. So that's one of the advantages for using vector. In fact, C++ provides not just a vector, but also many other containers. They call this kind of thing called a container. For example, you also have a queue container. You also have a map container that allows you to store hash maps, that kind of thing. And the containers is actually a very important feature of the standard C template, standard template library, or STL actually. And they have algorithms that's defined for those algorithm specific, very highly efficient as algorithm that's written for those containers. So vector is one of the containers that's used most often. We have been using cout for quite a while. We are using cout to print out some results to the standard output. But how do we actually get inputs from the standard input, for example, from the keyboard? So there's a counterpart to cout. It's called cin. Let's try to. So here we have two an integer and a long double. So let's try to sort of. The integer was initialized to 1, and the long double was initialized to some floating point number here. So let's try to sort of change their values, change the values that's stored in these two variables by using numbers from the standard input, or cin. You call the cin, you use the cin in this way. Cin represents the standard input, so the flow is going from the standard input to your variable. So here it's like two smaller than signs next to each other. So this is actually two larger than signs next to each other. So you want two inputs from the keyboard. So the first one is going to go into I, the integer, and then the second one is going to go into that long double, LD. And then you can just end the statement. Of course, you have to sort of print out some stuff so that the user knows what you are expecting. Enter an integer and a double, and then just a semicolon. For this particular line, I'm not using a end of the line here because I want the user to enter their input on the same line as the prompt. So here I'm just not using an end of line here. I'm just ending it with a semicolon. So let's just save it and then build it and then run it. Here it's gonna, after printing out the current value in I and then the current value in LD, it's asking me to enter an integer and a double. So if you click in the console, and then it's gonna ask you for you can type the number here. So suppose I type a number 12, for example, and then space, and then I'm gonna enter some kind of double. So I'm just gonna use some arbitrary number, and then just press enter. So now it's actually printing out the I plus LD using the changed value. using the value that I just entered. So it's 12 plus 323 dot something. So it's 325 dot something. But you can sort of see that lots of the numbers in the back were truncated. It's actually rounded. It's actually rounded. All those four numbers has disappeared. It has been rounded. It's not because the variables actually has lost precision. It's just because the cout has some kind of default behavior that doesn't actually print out that many digits or that many kind of precision. So what you can do is to modify the behavior of cout. You can change the behavior of the default cout by using some modifiers. For example, we can just use the function called set precision. And then the set precision function allows you to change the number of decimal points, decimal positions that you can actually print out in the cout. Suppose you want a precision that's like say 15, for example, and then it's gonna print out more digits. Suppose we save it and build it, and then let's just run it again. So we're gonna enter a double, and then some kind of integer. And then this time it's actually going to print out more digits. So set precision is one of the ways for you to actually change the kind of decimal points or decimal precision of the printout. So here you can sort of see I'm adding an integer to a long double. So what's going to be the type of the result? The type of the result is actually going to be a long double. Actually, it's so the compiler or the computer is going to sort of promote I to a long double and then add it to this long double. So the result is not going to be sort of automatically rounded, but the set precision is going to allow you to see more digits in the floating points. And suppose you would like to use the scientific notation. If you want to sort of don't use the fixed point, this kind of notation, but use scientific notation. So what you can do is to do another modifier. Let's call it scientific. So you just use the keyword scientific, use the word scientific to modify the behavior of cout, so it can print out the result in a scientific format. So again, let's try to save it. And then let's run it. And then long double. So now it's the number result of the add is going to be printed in the scientific notation. So these things allows you to actually modify the behavior of cout. And these two modifiers are kind of those that's used most widely, used most often. So if you would like to change the behavior back to fixed, you can use the function called fixed, and then whatever precision you want to use, say 20 or something, I plus, oh sorry, plus LD. So you have two ways for displaying a floating point. One is called a scientific, and then the other one is called a fixed. Both of them are actually functions for you to actually modify the behavior of the cout. So here's the scientific notation, and then here's a fixed point floating point notation. So the data types that we have been using so far are all built-in data types. So here's the integer, floating point number, double, long double. These four, the two strings and the two vectors, belongs to are in the standard template library. But you can sort of still consider them as built-in because the standard template library is like so universal. So you can just use those things without any sort of modifications. So you can still consider those as built-in. But suppose you would like to define your own data type. So how can you actually do that? Suppose I want to sort of define a data type. I can use the keyword struct. I'm going to define a data type that's called a person. So as soon as I sort of type enter at this line, so the ID is going to close the curly braces and put a semicolon behind the closing the right semicolon, the right bracket, bracket. So here I can actually define my own data structure. So if I actually think about those variables as containers, those vectors as containers, you can actually compose those smaller containers together into a bigger container. So here I'm actually defining a bigger container, and this bigger container have smaller containers inside of it. So a person is going to have a name. So I'm going to define a string, and that string is called a name. A person is going to have a name, and then a person is going to have an age, and the age is probably an integer. It's just an integer. So I'm going to define another variable or another container that's called age, and then a person is going to probably have a sex. So I'm going to define another string that's going to call it sex, whether it's a female or a male. So that's going to be some sort of basic information about a person, right? And once you have defined a data structure called a person, you can use it to define. You can use this structure to define objects or instantiate objects. So let's try to sort of use this person structure. So how do you actually use it? You use it just like you use those use a string or something. Use those building variables. So now you have a person data type, and then you can define a person that's called P. Now you can initialize it. So how do you actually initialize it? Still using the pair of curly brackets, but now you can sort of specify what's actually the name of the guy, the person, the age of the person, and then the sex of the person. So let's just say Bob. That's going to be the name, and then the age. The age is an integer, right? Let's get it like 30, and then the sex is a male. So now you have a object that's a person. So let's see if it's gonna compile. So it looks like the code is correct. So if you would like to change some of the properties or some of the values that's stored inside this person, how do you actually access it? Suppose Bob has just passed his 31st birthday. So you would like to change its age from 30 to like 31, for example. How can you actually do that? You can do that by doing p dot and then age, and then you just give it a new number, 31, for example. And you can also, that's how you actually change the values. And you can also sort of print out the values, for example, p dot name, and then concatenated with some string is p dot age, and then another years old now, and then end of line. So let's try to build it, and then let's run it. It's enter integer and a double. This is from a previous example, so I'll just give some number. So Bob is 31 years old now. So that's the printout from this particular line. And that's one of the basic ways for you to use a composite data type. That's called a struct. A struct is basically a class. So you can just replace this struct, with the keyword class, and it's going to function pretty much the same, except that you have to sort of say this is public. So the stuff that's sort of defining there is kind of public. So it allows you to, so a public, this keyword public just tells the user of the class that those variables can be accessed by anyone. It can be accessed by the user of the class. So you also have other keywords that's called private and protected. Those are sort of classifications about the accessibility of different names and functions. For struct, if you are just using the struct keyword, and then those variables are going to be default to public, you can just if you are using class keyword, the variables, if you don't use the public keyword, those variables are going to be default to private. So nobody, so the users cannot sort of access those variables directly. But if you actually use the public keyword, those are going to be variables that can be used by the user. So let's try to build it again. But before we do that, let's comment out these two lines, because I don't wanna always enter the integer and the double here. So let me just save it, and then let's build it, and then this time let's run it. So Bob is 31 years old now, so it has come down to this particular line. So you can use either a class or either using a struct, right? The only difference between a class and a struct is the default accessibility for variables. So for a class, those default behavior is sort of keep the variables as private, unless you specify the public keyword for it, for those variables. But for the struct, the default is to keep those variables as public, so other people can access it. And for now, this particular class has just data members. Those are all data. At the beginning, previously I was telling you that a class is sort of a combination of both data and functionalities and functions that can apply on the data. So you can also define functions, introduce functions into classes. So you make it a sort of a more complete class. But we'll do that in a later video. For now, let's just do some simple examples. Let's do some still quite simple examples. One of the very interesting feature of the latest C++ is universal initialization. So here I'm actually initializing P, initializing a person with the name, age, and sex, and the order has to be sort of similar to the ordering of this of how those variables are listed in the class definition. So it's gonna universal initialization is gonna automatically pair those inputs to the variables that's you listed here. So it's gonna pair Bob to name, and then int 30 to age, and then sex to male. So if you actually switch the two different variables, for example, if I put a male here and then Bob in the end, it doesn't really know this is actually the name, but this is the sex. It doesn't really know. It's gonna pair male to name, and then Bob to sex. So the ordering is kind of important. If you don't believe me, we can just compile it and run it. So now it's actually printing out a male is 31 years old now. So it's actually telling me male becomes the name of the person. So that's not exactly what you wanted. So you have to be careful when you actually initialize the particular object or particular class using uniform initializer. So you have to really take a look at how the class is actually written before you can actually sort of determine what's gonna be the correct ordering of the information that you put into the initializer. Your own composite data type can also contain other composite data type. For example, if you would like to add a vector to your person class, so suppose you would like to add a vector of floats, that's called vitals. So it's gonna contain the vital signs, for example, the heart rate and your blood pressures for this particular person. Then you can just do that. You can add a vector of floats into your person class, and the name is going to be called a vitals. And in the initialization list, you have to add one more you have to add one more input, which is actually a vector of floats. So you have to add a vector of floats. But now you don't really have to give the vector floats a particular name. You can just use the initializer, universal initializer list, and then just put the numbers in there. Suppose your the heart rate for Bob is like a 75, and then the blood pressure is like say 120, and then 90, that kind of thing. So that's sort of the vital signs for Bob, for this particular person, and then it's gonna compile. So now you have one more. It has finished without any errors. So now you have one more object in the initialization, one more input in the initialization list. So how do you actually access that kind of information, right? You can just print out so p.vitals, and then if you want to look at the blood pressure, look at the heart rate, for example, it should be 75, and then give it a space, and then p.vitals. That's one of the blood pressure, and then another space, and then p.vitals. The last. So now let's build it, and then let's print it. Bob is 31 years old, and now so that's the 3 numbers in the vitals. You're seeing too many digits. That's because we have changed the precision to like 20 here. So once you actually change the behavior of cout, you have to change it back if you want to reduce the number of precisions. So here I'm gonna do set precision. Let's just give like a 7 or something. So now it looks more reasonable. The number of digits is sort of more reasonable. So that's how you can actually put a composite object. This kind of vector of floats is a composite data type into another composite data type. You can sort of again, you can also define vectors of person, for example. So in this kind of case, how do you actually do that? You can define vector, but inside of this square bracket, you can use person as a vector, p, for example. So if you would like to have like a AP, for example, area of persons, and suppose you would like to have like an array for 3 persons, for 3 people, and then you can just put a 3 there. So that's one of the ways for defining vectors and sort of initializing the storage for. So the number 3 here is sort of how many persons you have. So if you actually cout ap.size, for example, it's gonna show you 3. So suppose you would like to have like 30 persons, then the size is gonna be 30. So the size is going to be 30 now. So that's, if you would like to initialize every element in this vector of persons using, for example, the same kind of information as you used for Bob, you can also do that. All you have to do is to sort of again use the universal initialization, the curly bracket, and then just specify the information that you want to use for initializing it. Suppose you want to use the name Kevin, right? You're going to use the name Kevin to initialize the name, and then you're going to use the age, for example, 25, as and then you're going to use the male as the initializing string for sex, and then another vector, for example, vector float the vitals. I'm still going to use the same numbers, 75, 120, 90. So in this particular example, you're going to initialize 30 copies of Kevin with this kind of information in it. And how do you actually make sure that it's correct? So let me just print out, for example, AP, the last element, some information about the last element. The last element here it's 30, right? So the last element is going to be 29. I want to look at its name, for example. So is AP29 the age years old. And then if I want to use the end of line, and then see out if I want to look at AP29's vitals, for example. For example, the heart rate. The blood pressure. Right. So let me save it, and then let's build it. So Kevin is 25 years old, and then that's the vitals for Kevin. In fact, you actually have 30 copies of exactly the same information. It's all the copies has been initialized to this particular set of information. And if you want to change, for example, the first one to a different set of information, for example, for a different name, for example, Carl or something, some other people, you can just change that. In practice, you probably want to change that in a loop without doing that by hand or by reading from a text file instead of typing the information on the keyboard. But this is just showing you how you can actually do a vector of persons and then specify the number of persons you want and initialize this particular vector with some dummy initialization information. And this is an example of a vector composed of persons, and we can also do vectors of vectors, for example. So you can nest the vector data structure into itself. For example, if you want a vector of vector composed of all floats, for example, what exactly is a vector of vector? A vector of vector is essentially like a matrix, but the different rows of this matrix can have different number of elements. It is possible to have identical elements, then that's exactly the same as a matrix, but it's also possible to have a vector of vectors, and each row of this matrix has different number of elements, for example. So so don't forget about put a space. Don't forget to put a space between these two larger these two left angle brackets, because if you actually forgot about this, and then it becomes exactly the same as this operator, the sing operator, the stuff that we used when we're reading from the standard input, and C++ is going to treat it as a mistake or error. So let's try to define a matrix, for example, a matrix of floats, and then we can initialize it. How are we going to initialize it? First of all, let's specify how many rows we're going to have. Let's suppose we're going to have 3 rows, and each row is composed of another vector of a float, another vector float. And for this vector float, we're going to initialize it to be like 1, 2, 3, 4. So this is essentially a 3-row, 4-column matrix, and each of the row of this matrix is composed of 1, 2, 3, 4, like these kind of 4 numbers. And we can sort of try to print out some of the values. So suppose we want to print out MF 0th row. That's the first row, actually, 0th row. And then let's look at the first element. That's 0th element, actually, 0th element. So so MF 0 with the first set of square brackets actually gives you the row. And then if you want to look at the first element inside of the first row, then you have to append a second square bracket pair with the index that's sort of inside of it. That's how you can actually index a matrix or something. And then suppose we give it a space, and then some random number mf. Let's look at the last one. The last row. The last row is gonna have a first index as 2, and then maybe the third column. The third column is gonna be 4. I think 0, 1, 2, 3, 3. Okay, so the printout should be 1 and 4. It's two numbers, 1 and 4. Let's compile it and then run it. Yeah, exactly 1 and 4. 1 and 4. So that's one of the ways for you to actually use a matrix, for example, inside of C++. Of course, if you want to do linear algebra, there's a very well developed C++ linear algebra libraries that allows you to use and develop and write your own codes. So there are plenty of that kind of libraries actually. If you look for those C++ linear algebra libraries, you can find many of them on the web. And those libraries can define their own matrix data structure, for example, right? So you don't really have to sort of use this kind of a syntax. You don't have to nest a vector inside a vector. So and you can just use those simplified matrix representation, and they may have their own memory management tools that comes with their data types, that kind of thing. But that's another way of using vector. You can use vector to actually construct a matrix. Right. Now, if we looked at these two examples, when we're defining an array of 30 persons, and then a vector of another vector, a vector of a vector of floats, a matrix of floats, you'll notice that here we are. What's actually following the variable name here is AP, and then here it's MF, is the parenthesis. Here it's parenthesis. It's a parenthesis. The syntax is actually quite similar to calling a function, for example. So here we're actually calling the set precision function a parenthesis, and then some input inside of the parenthesis. Here we're calling we're defining the main function, but there's nothing inside of the parenthesis. So if you actually pay attention to how I actually wrote these two lines, you'll see that the syntax is kind of similar to function calls. In fact, it's actually calling what we call the constructor. It's actually calling the constructor of this particular object. And for this particular object, it's a vector. And it's actually calling the constructor of the vector class. And here it's actually calling the constructor of the vector class also. And this constructor function takes on these kind of inputs. For this particular example, for these two particular examples are just the two input parameters. For this example, it's 30. That's the total number of elements that's going to go into AP, the total number of persons. And then the initialization value for each of the person, for each of the element that's going to be inside of your array. And the initialization value is inside of this initialization list, so enclosed by this pair of curly brackets. So here it's again, what you want is three elements for this vector. What's going to be the type of the elements? The type of the elements is going to be vector floats. So what you're going to have is 3 vector floats inside of MF, and then that's the second. That's going to be the initialization for each of the element inside of MF. What's the element of MF is what? Is vector floats. So what you're actually giving it as the initialization value for each of the vector floats is exactly a vector floats. But this vector floats has been initialized using this initializer list 1, 2, 3, 4. So essentially, this particular matrix is going to look like every row is going to have 4 columns, and every row is going to have the four values 1, 2, 3, 4. So it's just a 3-row, 4-column matrix with each of the row given by the value 1, 2, 3, 4. So you can sort of find the kind of a logic inside of this kind of inside of this kind of syntax. But we're going to look at how we can write classes using constructors. You have a constructor, and then you also have a destructor. So constructor can be used to construct the element, to construct the variable, and then to construct the object. I mean, and then destructor is going to handle how the object is going to be erased from the memory. How do you actually release the memory? That kind of thing. But for this particular very simple class that's called a person, we don't have a function. We don't have a we did not actually explicitly write a constructor. We did not explicitly write a constructor or destructor, but the system actually automatically generates constructors for you. Every class actually has a constructor, so it's not visible to us right now, but we can write our own constructors or destructors, and so if we look at the outline on this on this particular panel, it's showing we have a header file, we have a main function, and now we have a class. So this is a symbol for class. That's called person. And then if we click on this triangle, it's going to show you the parameters, the data members inside of this class. And then we'll have a main function, right? But for now, we have just a single function inside of our source code. We can write our own functions also. We can write this is our own class, right? For now, we're just treating the class as a kind of a personalized data structure. So you can define your own data structure, right? But it also allows you to write your own functions. Let's try to write some personalized functions also. We can define our own functions. Now let's write a function of our own. How do we actually define a function, right? So just like you define a int main here. So this time let's try to write a function that's going to return a float, and the name of the function is called add, and then it's going to take two floats, float I and then float j. Maybe not a I and j, maybe f and g for example, float f and float g for example. And then we're going to just the function is very simple. It's just going to return f plus g. That's it. So you can sort of see the definition of the add function, and you can compare it with the definition of the main function, right? So you have a return type. You have a name for the function, and then you have a parenthesis here. For this particular example, it doesn't have anything for main, but it has two input parameters for the add function. And then for this add function, it's going to return f plus g, and for the main function, it's just going to return 0. So it's returning an integer, but here it's returning a float. So how can we actually use this particular function, right? How can we use this particular function? Let's just use this particular function inside of the main. So here I have defined a bunch of numbers. So let's see if we can actually let's just some identifier. I'm going to call the function add with f and d, for example. So in this example, I'm calling the add function here. I did not give the output of the add function a particular variable name, but it's going to be printed out. But it's going to be the result is going to be sent to cout, so I can sort of see the output of the add function call. And then the variable, the input variable, the inputs that I'm feeding to add is f and d. So f has a value of 3.14, and it's a float. D is also a float, but it's actually a double precision float. As you can see, it's a double. So when the system actually calls the add function, it will sort of convert this double to a float actually. So there is an implicit type conversion here. It's actually converting a double to a float. So the number that's being stored in D is going to get truncated. It's going to be converted into a float, and that floating number is going to send into this particular floating number G inside of this add function. And this f, the value that's stored in f, is going to be copied into this variable. Although it's also named as f, but it's actually different memory location actually. So basically you are copying the value inside of f into a different memory location, and that different memory location also has a name that's called f, but this f is different from this f. This f is sort of the f that's defined here, and this f is defined right here. It's float f. It's defined in the function. In the input list of the add function actually. The input list of the add function. So it's two different memory locations, even though their names are sort of exactly the same. So the values inside of this f 3.14 is going to be copied over to the memory at this f, and then the value for d, that's 3.14. This value is going to get truncated to the width of the float, and then get copied into the memory of g. And then the floating point, the add function is going to add these two floating point numbers together, and then return the value. And the return value is going to be printed out on cout. So let's run it. So that's the printout. It's 6.28, about 6.28 or something. So that's how you can actually use a user-defined function. You can define a function just like that. But suppose we would like to add these two strings together also. So what are we going to do? We can write another function, for example. We can write another function. We can also call this particular function called add, but it's going to return a string this time. And then it's going to take us two strings. It's going to take two strings as input, and then it's going to return what? S1 plus S2. So it's going to take two strings as input and return another string. That's just a concatenation of the two input strings. So now if we actually print out, if we do a cout, still add, we can call this add function S1, S2, and then end of line. So you can sort of see that here I'm calling the add function with two floats as input, and here I'm calling the add function with two strings as inputs. And the function name is exactly the same as add, and it works. So if you don't believe me, let me compile it, and then let's just run it. So here it's printing out the add of two floating point numbers, and then this is a concatenation of two strings. So this particular behavior is called function overloading. It's just like operator overloading. You can overload a function as long as the input parameters and output parameters are different. Those two functions are treated differently. So C++ actually has the kind of intelligence of picking the right add function to use. So a function is not just identified by its name anymore. It's also identified by the input parameters for this particular example. When you are feeding the add function with two floats, C++ actually knows to call this particular function. And if you are actually feeding it with two strings, C++ actually knows to use this particular function automatically. So that's what we call the function overloading. It's a quite powerful thing in the C++ language. It allows you to overload functions.